Good day, everyone. These few clips, these few slides will give some review examples of something that you hopefully practiced in Gen Chem 1, General Chemistry 1, and that would be grams to moles, moles to grams, molarity, and the like. So, goodness, what is a mole? A mole is I call it the chemistry dozen. It's a large number of particles. It's the way we connect what we can't see to what we can see. If we imagine, I think it's 602 billion particles or something like that. There's no way we could possibly count them, but we can certainly weigh them on a scale. And using the knowledge of relative masses of elements and compounds, we can, in a way, count by weighing. A method of counting by weighing. And that's how we can compare amounts of substances, amounts of water, amounts of sugar, amounts of carbon dioxide. So let me scroll down just for a second to remind you where I'm getting these numbers from the periodic table. It's not the atomic mass, the main whole integer number, like 1 or 2 for helium or 10 for neon, 11 for sodium. It's the decimal number, which is an estimate of an atom's atomic weight, molar mass of a mole of that element. It's actually all relative to carbon, 12.00. Anyways, that's a whole nother lecture. But in any case, I look up these masses, relative masses, and I apologize for the clarity of this table, but take water, for example. What's the mass of 1 mole of water? Well, from the table, I usually go 3 sig figs. Hydrogen weighs 1.01, but there's 2 hydrogens, and oxygen weighs 15.999 something, and that comes up to close to 16 grams per mole for oxygen. So for the compound water, I just add up the elements' molar masses, formula masses from the table, 18 grams for a mole of water. 18 grams for a mole. Here's a simple sugar, C6H12O6, 6 carbons, 12 hydrogens, and 6 oxygens. That all adds up to 180 grams for a mole. This one's 10 times bigger than this one. I guess this molecule weighs 10 times more than this molecule. Here's a formula unit of a salt, copper 2-sulfate pentahydrate, copper, sulfur, 4 oxygens, that little 4 oxygens, 5 waters. I used from above the 18.0 number for water. There's 5 waters, and that all comes up to very close to 250 grams per mole. And of course, this unit is larger than this unit. Here's a really large unit cell of a superconductor: yttrium, barium, copper, oxygen. Add them all up. It's simple math, but it's always a challenge not to make a mistake. And you say, well, that's all an interesting game, but how is it useful? Why am I doing this? Well, the primary reason is if you're able to weigh a substance on a scale, like 75 grams of water, we divide by the molar mass, 18 grams per mole, and we get a way to count a number of particles. This is 4.17 moles of water. That's a way of saying 4.17 times Avogadro's number, 6.02 times 10 to the 23rd particles of water. Oh, by the way, conversion. What did I do? This is sort of a random number, 75. I could make up any amount of water I wanted to and divide it by 18 grams per mole. I put the grams on the bottom, so the grams here cancel the grams here and leave me with moles as a unit. Is a very common technique that chemists use quite frequently. 43.2 grams of copper sulfate pentahydrate. I totally made that number up. From above, we found it was 250 grams per mole. So I put the grams of my conversion factor. In a way, I can call this a conversion factor. It's a molar mass. Put the grams on the bottom, moles on the top. 43.2 divided by 25 gives a small number, 0.173 moles of the copper sulfate pentahydrate salt. So if I had a recipe or a balanced equation or some literature I was referencing, I could actually use these masses and my knowledge of how to change grams to moles to come up with the correct amount of a substance to use. Sometimes you'll be given the molar mass. They might tell you the molar mass of water. You might be told the molar mass of copper sulfate, or sometimes you might have to figure it out for yourself. 21.7 grams of copper 2 nitrate trihydrate, copper, 2 nitrogens, and 6 oxygens, or I could use, say, 2 of those nitrate units. So the nitrate unit is 1 nitrogen and 3 oxygens, and 3 waters along with that as a kind of a hydrated salt. This is the salt, this is the hydrate, goes along with it. In any case, I didn't even bother to write that down, but whatever that adds up to, that's the number, it's the molar mass, it's the grams per mole weight of 1 copper nitrate trihydrate unit. So 21.7 divided by this sum gives me, again, a small number of moles of that salt. Now, let's see. Or we can go the other way. What if a recipe in a reaction called for 1.71 moles of ammonia? Well, in that case, I put the moles of my conversion factor on the bottom, and I go look up 1 nitrogen and 3 hydrogens. That adds up to 17.03-ish. So 17.03 grams, the moles cancel, and times 1.71 gives me 29.1-ish grams to 3 sig figs anyway. I had 3 sig figs over here. 21.9 grams of ammonia. By the way, it's hard to weigh it, to mass a gas on a scale because they're so fluffy. But we'll talk about that a little bit later. What if an industrial process called for 5,000-ish moles of this hydrocarbon? 5,171 moles. Can I weigh that in grams? Well, I have 10 carbons. I have 8 hydrogens and 1 oxygen in this formula, and that's a grams per mole mass. So I add up those numbers, 8 times that, 16 of those, 16 grams there, 10 of those, times 5170. Oh my goodness, comes out to a big number. What is that? 745,000 grams if I round to 4 sig figs. 4 sig figs? Oh goodness. Well, whoops. This is 12.01 actually. If I stay with 4 sig figs, perhaps I should have paid more attention to my sig figs up here. But indeed, I think if we round it appropriately, it's very close to 7,450 grams, or 7,450 kilograms. Big number. Or we can go the other way. What if I had a small number? Oh, I apologize. I got chopped off here a little bit. That's a grams on the right-hand side. 0.0537 millimoles. My goodness, a milli is 1/1000th of a mole. In any case, I can leave the milli there and just take 17 carbons, 19 hydrogens, 1 nitrogen, and 3 oxygens. And that gives me the molar mass in grams per mole of this compound. Oh, I see. It's a pain medication. And I take the 0.0537 millimoles, the moles here cancel with the moles here, times this large molar mass, and I find the millis survived the conversion. The millis did not cancel anywhere, and so instead of grams, I get milligrams. So 0.0537 times that large number gives me 15.3 milligrams of pain medication. All right, but what if we can't really weigh it on a scale? Much of chemistry is done in aqueous solution. And if that's the case, I have to use this definition of what's called molarity. Molarity is moles of solute dissolved in liters of solution. Excuse me. Or in other words, if I had a molarity and a volume of liquid, I could multiply those two to find the number of moles. This is a very, very useful definition. Memorize it. It's used all the time because much of chemistry is done in aqueous solution. Here's an example, 5.25 liters of a 0.983 molar. So molarity times volume's in liters, or it can be in liters. gives me a number of moles of substance altogether. In that 5¼ liters, I would have 5.16 moles of this dark purple staining oxidizing agent. Another example, molarity times volume. Here I didn't change to liters right away, but my milli then survives. So 45.3 times 1.1 gives me 49.8 millimoles of HCl. Or in other words, if I had changed this to 0.0453 liters, then that would have immediately or straight away given me the 0.0498 moles of HCl. Here's another example. Here's a fun compound. 1.07 microliters times 0.0952 molarity gives me 0.10186, etc. If I round it off a little bit, and don't forget my micro, the molarity times volume gives moles, but I have a micromole. Wow, that's a small number of moles, 10 to the negative 6. And if I write it in formal, correct scientific notation, 10 to the negative 7. Just for the fun of it, looks like I included some models of adrenaline, epinephrine. Who doesn't like a little adrenaline in the brain? All right, so we can also use molarity as a conversion factor, which is very handy. I think it's very handy to get in the habit of thinking of it in some ways. The conversion factor, the definition of molarity is moles per liter. So if I look at 0.952 moles per liter, for example, nitric acid, I want the volume that contains 0.571 moles of this acid. There are two ways to look at this one. What volume of 0.952 molar acid contains 5.71? Well, I wrote the 5.71 moles because that's what I wanted. And my 0.952 molarity, that's moles per liter. Moles per liter. This comes from right here. But I wrote it upside down, so my moles would cancel. 0.571 divided by 0.952 gives me a number of liters or milliliters. We can look at it the other way. Another way to look at it is just going back to the, the definition of molarity. Molarity, if I flip-flop these two, molarity is moles per liter, moles per volume. So I could just take my moles that I was requiring divided by the molarity. Gives you the same answer. But I like this better because it shows how the units cancel. And I don't have to memorize this as long as I know what molarity means.